Okay, on problem 1 here, it has us looking for hidden behavior. Now, I don't want to instill paranoia to the point where you feel like you have to look at every problem like we're about to look at this one. But when they bring up the fact that there's hidden behavior, it's worth talking about and worth looking at. So what's the possible hidden behavior? Does this graph hit the x-axis once, twice, or not at all? Because the perspective I have from here is it looks like it hits it maybe once. Okay, so we're about to take a closer look at our calculator. Okay, so I've taken the time here and I've keyed in the equation that's told to us on this problem 1. And I just have a normal window, zoom 6. It's the 10 by 10 window that matches yours on the paper. And it looks to me like I'm seeing the same thing kind of as it was on my paper. So does it hit once, twice, or not at all? Well, the first thing you could possibly do is kind of have a window that looks more in on this area right in here to tell that. So maybe I go from 0 to say 3, and from say -1 to 3. You know, just something that zooms in on here. And let's see if that does any good. It may or may not. So a window from like 0 to 3, and from maybe -1 to say 3. Now that actually wasn't a bad choice, because if I was watching there, I saw it graph underneath the x-axis. But I'm just going to prove it to you a little bit more clearly by bringing in zoom and then move this kind of in this region here of where I think that minimum is. And well, that actually makes it look worse a little bit. Let me go back and zoom in again. I just have to move it again and then push enter. And you can actually see that I was above the x-axis there, below it there, and above it there. So either way, I realize there's 2 zeros here. Somewhere in this region it's hitting the x-axis, and somewhere in this region. So now to find those zeros, we can do second trace, 0, and be left of one of them. Since I'm not sure what my window settings are anymore after using zoom in, I have to just use the scroller and say that is clearly left of where it hits the x-axis, and over here would be clearly right of where it hits the x-axis, and somewhere in between here is where it hits the x-axis. So the 0 is actually at 1.5, 0. And then I would rinse, lather, repeat that for this 0 over here, second trace, 0. I am currently left of it. Any place left of this other 0 would be fine, so I'll push enter there. Any place right of the other of that 0 would be fine. Just make sure you're right of it. I'm not sure I'm right of it until I'm right about there. And then back somewhere between there, I think it hits the x-axis, and it's at 1.6, 0. So there are your 2 zeros that we couldn't see from a standard window. It was hidden. Again, not trying to instill paranoia about things. You know, does it hit more than once? But it is something worth understanding or worth checking into to make sure you know, does that just come down and hit the x-axis, just bump it? Or does it actually pass through it and we can't see it from here? Does it not hit it at all? Does it just kind of get close and then not hit the x-axis at all? Therefore, there would be no x-intercepts. So, worth noting, but don't lose sleep over it. Okay, we're going to answer these 4 questions just all together, all in once. Seek out the dominant term. The dominant term is the degree with the biggest exponent, the highest degree of the polynomial. So the dominant term tells you everything you need to know about end behavior. If that dominant term has an odd exponent, the ends will go in opposite directions. If the lead coefficient is positive, it'll go up to the right. So that is C. Find the dominant term. If it's even, the ends go in, if the exponent is even, the end go in the same direction. So they'll both be up or both be down. The fact that this is a positive 3.08 means that they both go up. Number 4, find the dominant term. Well, there's only one term, so this is the dominant term. The exponent is odd. Therefore, they'll go in opposite directions. The lead coefficient is negative. Therefore, the more I go to the right, the more it goes down. So the more I go to the right, the more it goes down. D. Number 5, look for your dominant term. Dominant term is right here. It is an even exponent. Both ends will go the same way. It is a negative coefficient, so they'll both go down. Okay, so on number 6, I certainly hope we use our knowledge about polynomials and the number of turns and the number of zeros to answer this instead of like graphing every single one. You could be here forever trying to do that. So let's start with A. A is a degree 5. That means that it could have 4 turns. Doesn't have to, so 2 turns is a possibility. Okay. It could have 5 zeros, 5 places where it hits the x-axis. But it could have less. So far, I'm thinking A is still okay. -5 is the y-intercept, and I know that because if you let x be 0, that would be 0, that would be 0, that would be 0, that would be 0, and all these zeros added or subtracted from each other would be 0. Then -5 would be -5. So we would know that the y-intercept is at -5. So this is a possibility for this graph. Let's go eliminate some others. Let's look at B. I know B is wrong just simply based on end behavior. The dominant term here has an odd exponent. That means opposite ends, opposite directions. Negative would be down to the right. So as I go to the right, this thing's supposed to go down. It doesn't do that. So B is out. Okay, what about C? C has a positive odd degree dominant term, so the end behavior is proper, up to the right, down to the left. Could be. Okay. Oh, wait. The y-intercept, if I let this be 0, this be 0, this be 0, the y-intercept is 5. Does this hit the y-axis at 5? No, it does not. So that takes that one out. Okay. Let's go look at D. Proper end behavior, positive odd exponent would be up to the right, down to the left, so that's good. Has a y-intercept of -5, yes it does. Could have 2 turns, yes it does. Could have 3 zeros, yes it does. So what I have to do is graph probably these 2 to convince myself that it is this one and not this one. But we'll do that here in a second. Okay, so I have entered those equations and I've set my window to the same window, I think it's just a standard window, that both A and C have. Okay, and we're going to hit graph. I'm not going to graph both these at the same time. That would be confusing. See how this one's turned off? I'm going to graph this guy first. Okay, and so we'll hit graph. And I very quickly realize that does not match this graph. Okay, so it's not A. Now let's prove to ourselves that it is C. I'll turn this one off now, turn this one on, graph it, and that is a distinct match to that graph. Okay, so if we look at the dominant term here on A, it's even, which means the ends should go the same way, and these ends do not go the same way. So it is not A. If we look at the dominant term of D, it is even, they should go the same way. It is negative, they should both go down. These ends do not both go down, so it is not D. And if we look at the dominant term of C, it has a negative odd degree, and a negative odd degree should be the more we go to the right, the more it should drop off. So that doesn't happen here, so it is not C, and the answer then is B. On 8, we have the dominant term. We could probably eliminate D because those ends should be going both up. We can eliminate A and C because both have a constant term, a y-intercept at -12, and this graph does not have an y-intercept at -12, so both A and C are gone. The only one to have the proper end behavior and the proper y-intercept is B. Okay, so I'm looking for definitely an odd exponent since the end behavior is in opposite directions. So that takes C out, and that takes D out. And the remaining one has a negative dominant term, which would be down as you go to the right and up as you go to the left, which is what this graph does. So the answer is A, because this one should go up to the right and down to the left. Okay, we're going to graph number 10 and check to see if we can get a comprehensive window. A comprehensive window is a window that shows you all of the hills and valleys, all of the x-intercepts, and the proper end behavior. Probably the y-intercept in there too. So let's take a look. I'm going to go to Window. I am going to set the window, when they say -5 to 5, that's the x-min, -5 to an x-max of 5. When they say by -5 to 5, that would be the y-min, -5 to the y-max 5. Okay, let's see what this looks like. This is not a comprehensive graph because I do not see the hills and valleys that happen between here, so something happens down off the screen. Not good to have that window. Let's go to Window and let's try B. From -3 to 3, and from -10, oops, not on the scale. Let's go with the scale one. -10 to 5. This is a comprehensive window. This is the one we'll accept because the end behavior of a 2x to the fourth should be both ends going up. Both ends going up. A fourth power should have 3 turns, or could have as most 3 turns. We've got a turn, a turn, and a turn, so I know it's not going to ever turn again. It could have as many as 4 zeros, although I'm convinced that this only has 2 zeros. Okay, and I see the y-intercept, the x-intercepts, all the turns and valleys, all the hills and valleys, and the proper end behavior. So that's a very comprehensive window. We'll say the answer is B. Okay, so we'll try and find the appropriate window to see a comprehensive graph of 11. And we'll do that by entering the equation and then going to Window and then setting that to that option A of -10 for an x-min, +10 for an x-max, -100 for -100 for an y-min, and 100 for a y-max, and hit graph. This is not a good comprehensive window because I don't see the top of the hill up there. So let's try something that's going to go a little bit further up, if you realize that. So that's I'm gonna jump me to C and say the window maybe is -6 to 6 and -10 to say 200. And perhaps now I'll see this a little bit better. This is said to be a comprehensive window because with odd degree, the end behavior should be up to the right and down to the left because that's positive. So up to the right, down to the left. It should also turn at most 4 times. There's 1 turn, there's 2 turns, there's 3 turns, there's 4 turns. It could have hit the 0, or could have hit the x-intercept 5 times, but I see it doesn't hit that many times. And it also shows me that the y-intercept is at 10, and I can probably see that that's 10 there, or at least that it's reasonable. So this is a nice comprehensive window to see this graph from. The answer is C. Okay, on number 12, can we eliminate some options that this graph right away is not? One of those options based off of D, showing it negative end behavior, negative odd degree, is down to the right and up to the left. That is not what this graph is, so let's get rid of it. Let's look at eliminating A, because the y-intercept of A is 5, and we see here about 5. We don't see any kind of graph at all. So let's eliminate A, which brings us to C and B. Now actually, I don't even need to take a calculator to graph this, because C shows me one location where it says it's decreasing. B shows me 2 locations where it says it's decreasing. I think it's only decreasing through the interval right here. So since that's the one interval it's decreasing, we don't have 2. So I think the answer is C. Okay, on number 12, or number 13, excuse me, we are going to definitely be able to eliminate B as a possible option because of the negative odd degree, knowing the end behavior should go in opposite directions. It does not here, so B is out. We could eliminate D because odd degree should go in opposite directions. This does not. D is out. And then we're left with A and C. Okay, and then simply put, if we're left with A and C, if we notice that A has a negative coefficient on the dominant term, therefore the ends should both be going down instead of both up. So the answer is C. Okay, so entering some word problems here. Most of the work is done by the calculator. Number 14, the following polynomial approximates the rabbit population in a particular area. R of x is given, where x is the number of years from 1975. Use a graphing calculator to describe the rabbit population from the years 1975 to 1990. Now, what we're going to pay special close attention to is this wording right here, where x is the number of years from 1975. So the year 0 would be 1975, the year 1 would be 1976, the year 2 would be 1977, the year 3, 78, and so on and so forth. So when we get our calculator out here and set our window, we might say set the window from 0 to 15 to represent the years 1975 to 1990. That's about the only trick. So we'll get the calculator out here and see what we can do. Okay, so we got the calculator going here, got the equation plugged into the calculator. One thing I noticed, our window is going to be pretty weird. We're going to go from year 0 to year 15 because we go from 1975 to 1990. The other thing that I know is that the y-intercept of this guy is rather large because the plus 4,500. So we may want to have this thing, the number of rabbits, go all the way up to like 6,000 or so. Just something more than 4,500 in case this increases from 4,500. Okay, so let's take a look. Yeah, I don't even see all the years there. If I set my window to say, I don't know, 10 or 15 or 1,000 or so, let's go 15,000. I might see, or at least have an opportunity to see this thing continue, and it's even crazier than that. But we can definitely see that from 1975 to 1990, that the rabbit population is on the increase, and that's the only question: is what's it doing? It's increasing. Number 15, the price of an electric guitars has varied considerably in recent years. The data in the table relates the price P in dollars to time T in years, where T equals 1 corresponds to 1988. Use a cubic function fitted to the data to predict the price of an electronic guitar in 1997. Now this problem is very similar to others we've done in the past with linear functions and quadratic functions. So let's break out the calculator and enter this data in our calculator like we have done in the past. Okay, so I have gone to Stat and Edit, and I've put the 1 through 9. Now notice we did not put the 1988 to 1996. It says to use 1 through 9. And then 618 all the way down to the 783, put that in the other list. We can now make this bigger so you can see this a little better. Okay. And then we've been here and done this before. Let's go to Stat Calc. Now in the past we've done linear regressions, and in the past we've done quadratic regressions, but it actually tells us on this one to do a cubic model or find a cubic function. So we're going to do a cubic regression. And then answer all these questions just as we always have. Hit calculate, and voila, here's the model, here's the numbers for that model. And so I'm gonna leave this screen up and then show you what we do with that from here on. Okay, so I have copied from my calculator screen here and created a guitar function, if you will, so that we can use that. Move this out of the way. Okay, I guess it'll be out of the way over here. It says find the price, predict the price for a guitar in 1997. So we're going to just simply figure out that 1997 would be T is 10. And therefore we can just find the guitar price at the value of 10. And we can enter all that into our calculator. Negative 1.5 times 10 to the third plus 16.4 times 10 to the second minus 12 times 10 plus 653.1, and get that the price of a guitar in 1997 is $673.10. Okay. I may show you quickly how we can do this with the calculator without, again, doing all of this writing down business. While it's still on the calculator, it can be quicker. Okay, so if you don't like to transfer all that stuff back and forth to paper and back and forth into your calculator, there's really no reason you have to do that. We can go simply to y equals, clear out anything that was there, and if you've done the regression recently, you can then go to vars. We can go to statistics. We can go to equation. We can go to regression equation. And it took and magically pulled all that equation that we just wrote down some of that to into the y equals. And then we can say graph. And I'm not sure I'm a fan of this window for this graph, so I'm going to say, let's go look at it from a standpoint of 0 to 15 is fine, but we don't need to go all the way to 15,000, whatever that was doing there. I think the most the guitars cost were somewhere in the realms of $800, so I might even say just go to $1,000. And let's take a look at that. Yeah, the guitars went up for a while and then prices dived off. Now, since we want to find the value at year 10, we can just say second trace value and enter the value of 10. And there's another way to get 670.47. That might actually be a little bit more on the precise side because we kept all of those decimals along the way instead of rounding to the nearest tenth. All right, I'm going to assume that if you're looking at 16 on this actual worked out key, that you have kind of looked at 15 and others, but you want to put 1, 2, 3, 4, 5, 6, 7 in list 1 of stat edit, and these values for the population in list 2. And then you're going to want to find a quadratic model, it says. So let's do stat calc and then quadratic regression. Now you do that to a point, and my calculator says that my model would be y equals 672.62 x squared minus 7,863.10 x plus 64,071.43. And so that is the said model, but the question says, oops, let's try and keep that together there. The question actually says, use that model to predict the population of 2000. Well, if I would keep going with this, I believe 1997 would be 8, 1998 would be 9, 1999 would be 10, 2000 would actually be 11. But let's write those out. 97 would be 8, 98 would be 9, 1999 would be 10, and the year 2000 would actually be T11. Okay? So then we just simply substitute 11 in for all of the x's. Entering that into my calculator, I get 58,964.35. Now there's definitely going to be some variation in those answers depending on how accurate you keep your information. If you do this using the calculator, okay, the way I showed you kind of in problem 14, you keep all of that precision along the way, and therefore you probably close in on a little bit different answer. I would just ask that you kind of, keep 2 decimals at least, and if you kind of jot down your work, that'll help clean up the communication of how you arrived there, because there could be dollars or cents off depending on how you round. So. All right, so number 17, we have to pay special attention to the directions here. They say take 1900 as 0, as the year 0. So 1950 should go into our calculator as 50, 1960 is 60, and so on. It also says determine whether the linear, quadratic, cubic function are the ones that fit the data the best. So we'll bring this back in here where you can see it. Please notice how I put in 50, 60, 70, 80, 90, and 100 to represent those years. Entered the data. Now we're going to start with the linear model and go stat, calc, linear regression. And we're going to pay attention to this r squared. Now if you don't have r squared on your calculator, you're going to do the following. You're going to go to second 0, which is the catalog. You're going to push the D button, which takes you into the D's. You can arrow down to a guy called Diagnostics On. Once you're at Diagnostic On, enter a couple of times, and it'll just say done. If you return to Stat and Calc and Linear Regression, you will now have the R. You shouldn't have to do that every time, only if your batteries would die or you have to replace them. Maybe that goes away. So now my R squared value is 0.92. We're looking for this to be really close to 1 or -1. If it's negative, it just means that it's a downhill kind of slope to that line. If this is close to 1, or the one that is closer to 1 is the best fit. So let's keep looking. I think there's a better fit. Stat, calc. Let's go to quadratic regression. Well, if we look at that, that's a perfect fit. A 1 is a perfect fit to a quadratic. So we could stop right here and write the equation y equals 0.1x squared minus 10x plus 440, and we would have the model. Now I do want to go on and show you something. If you go on and do stat calc cubic regression, it too will show as a perfect fit. But if you pay attention to this, it's saying A is 0. And therefore, if A is 0, this lead term here called a cubic is really not there, so it's really just going to be a quadratic. So don't go beyond it. If you find that a quadratic equation is a perfect fit, let's use that one. There's no reason to go look for the others. Okay? So I'm going to return to stat calc quadratic regression, and we're just going to write this down, and that will be our equation. Number 18, just a couple of things to note before you enter things into the calculator. It says take 85 as year 0, so start 0, 5, 10, 12, and 14 for the years. Put those into the calculators in list 1, 7, 12, 16, 19, and 20 in list 2, and then do your stat calc linear regression, quadratic regression, cubic regression, and quartic function. You will find that the quartic is a perfect fit, an r squared that's 1. Now my calculator, I had to actually scroll down to see the r squared, but it is there and it shows that that is 1. So then go back and write the equation, and you should have the same equation that I have, rounded to about 3 decimal places. Please note that the answer key is wrong on 18. It says that the best fit was a line, and I disagree with that. Okay, on number 19, we want to first realize that 1984 is year 0 and adjust those accordingly. Put that into the calculator, and then calculate the linear regression, the quadratic regression, the cubic regression, and the quartic regression. And we'll find out that the quartic is slightly, r squared is slightly closer to 1, so it's probably the best fit. And when you read your calculator on this one, be super careful, because my a value on this quartic function says negative 3.24 e to the negative 4. So remember, that means the decimal places moved 4 places to the left, so we'd have 3 zeros and then a 3. That's x to the 4th. And then we'd have minus 0.0660 x to the 3rd. Oh, I got that in the wrong place. Excuse me. I jumped onto the next line here. It's actually plus 0.0108 x to the 3rd, and then minus 0.0660 x squared, and then it would be minus 0.6502 x, and finally the constant is plus 7.6756. Now, the only reason that I kept that to 4 decimal places is because the first one kind of needed to show it, so I kept everything to 4 decimal places along the way. But just be a little bit cautious as you write that one, that you understand this first term right here was in scientific notation on the calculator screen. Okay, we can probably rattle through 20, 21, and 22 pretty quickly. Fill in the blank. The maximum number of local extrema, that's kind of turning points of the graph of a polynomial function of degree 9 is, well, you'll only have at most one less turning point than the degree. So since this is a degree 9 polynomial, it could have 8 turning points. Okay, could have less, but it might have 8. For the polynomial function given, what happens as x tends to infinity? So let's find the dominant term. As x gets incredibly large as we go to the right, I think we would expect this graph, since it's an odd degree with a negative lead coefficient, we'd expect it to dive downward. So it would head towards negative infinity. And 22, A polynomial of degree 5 has at least how many x-intercepts and at most how many? Well, we know it has at most the same as the degree. So it's going to have at most 5. And if you think about a fifth degree polynomial, eventually it has to go all the way up or eventually all the way down. Somewhere it's going to hit the x-axis. So the end behavior is going to cause it to have at least one x-intercept. Using synthetic division to decide, and the remainder theorem to find p of k, we will just simply synthetically divide with k being -2 into the 3, the -4, the -5, and the 12, and make room for synthetic division to happen. So we're going to bring down the 3. 3 times -2 is -6. -6 and -4 is -10. -2 times -10 is +20. Add, you get 15. You get multiply, you get -30. Add, you get -18. This guy on the end is known as the remainder. That remainder is also just so happens to be the value of the function at k. So we know the function has a value of -18 if you'd plug -2 into that function. Okay, so using the synthetic division and the remainder theorem to find the value of the function at 5. We'll bring the 1 down, multiply by 5, get 5, add together, get 3, multiply together, get 15, add together, get 19, multiply 19 and 5, and get 95, add together and get 97. This is the remainder. That is also the value of the function when 5 is plugged into the function, so it's A97. Well, this one looks like fun. Number 25, using synthetic division again, we bring down the 1, we multiply by -3, we get -3, we add together, we get -1, we multiply by -3, we get 4, no we don't either, we get 3, we add together, we get 1, we multiply together, we get -3, we add together, we get -6, we multiply, get 18, we add together, get 20, we multiply, get -60, we add together, get -65, we multiply 3 and 65 and get 195, we add together, we get 189. Okay, let's use synthetic division to find out if 3 is a 0. If it is, we will end up with a 0 in this spot. Let's see, bring down the 2, we get 6, add together, we get 0, multiply, we get 0, add together, we get 1, multiply, we get 3, and voila, we get a 0. So since we got a 0, 3 is a 0, so yes, it is a 0. But is 3 a 0 to this polynomial? Let's find out. Bring down the 5, multiply by 3, get 15, add together to get 16, multiply, get 48, add together, get 45. I don't like how this is going. 45 times 3 is 135, 137. That isn't a 0, so no, it is not a 0. 3 is not a 0 of that polynomial. Directions are a little weird on 28. It says sketch, but they're already all provided because I'm not going to have you actually physically sketch. You can just match to a graph. So sketch the polynomial function which has a negative y-intercept. Well, that throws that guy out. And that's probably the only one that gets thrown out by that. 1 local maximum, that is 1 hill, and 1 local minimum, 1 valley, 1 hill, 1 valley, a negative y-intercept, and has no absolute extrema, true because this goes down forever and up forever, thus preventing anything to be the absolute top or absolute bottom. I believe the answer is D. 29 is just simply reducing fractions. 8 halves, 8 over 2 reduces to 4, and x to the 7th over x to the 2nd. Remember, we subtract exponents if you have them in stacked, so it'd be 7 minus 2, x to the 5th. So 4x to the 5th is the reduced answer. Now on 30, we're going to split it into 2 different fractions. That would be easier than long division ever would be for this particular case. So it's 24x to the 6th over 8x, and it's also minus 40x to the 4th over 8x. Therefore, Therefore, we can do the same thing we did on 29 to both of these fractions. 24 divided by 8 is 3, and x to the 6th minus an x to the 1st would be x to the 5th, minus 40 divided by 8 is 5, and x to the 4th, take away an x, is x to the 3rd. So there is our reduced answer to 30. All right, let's go through the same thing here as we did on the previous two, where we split this into two separate fractions, 6x to the 9th over 5x to the 4th, but also, can do a better job of writing that 4, also plus 5x to the 5th over 5x to the 4th. And let's reduce those independently. 6/5 doesn't really reduce, so let's just call it 6/5. And x to the 9th on top of x to the 4th would leave us x to the 5th on top. And 5 over 5 is 1. And x to the 5th over x to the 4th would be x on top. So one might just say 6/5 of x to the 5th plus an x, if you so chose to do it that way. Okay, we're going to use long division here on this problem. So the first thing to note here would be to set it up properly. Negative 3x plus 1 on the outside of the box, and negative 6x cubed minus 7x squared minus 12x plus 5 on the inside of the box. And we're going to go by asking ourselves, what do we take times negative 3 to get negative 6x cubed? And I believe that would have to be 2x squared. And then 2x squared times literally negative 3x is negative 6x cubed. And 2x squared times 1 is as well 2x squared. We will change the signs. Change and change. And we will add down. Okay, we're going to add down and we get nothing. And we also get negative 9x squared. Bring the next guy down. And we're ready to rinse out the repeat starting over. What do I take times negative 3x to get negative 9x squared? That would be positive 3x. Positive 3x times a negative 3x is negative 9x squared. Positive 3x times 1 is positive 3x. We will change the signs, and we will add down. We will get negative 15x. Bring the next term down, plus 5. Move your paper up. Make some room. Hold on. There we go. Now it's cooperating. Okay. And what would we take times negative 3x to get negative 15x? And that would be a positive 5. Positive 5 times a negative 3x is indeed negative 15x. Positive 5 times 1 is 5. Change the signs. Add down. Just so happens we don't end up with a remainder. So the answer to this long division is 2x squared plus 3x plus 5. All right, 33, let's long divide. We've got x plus 3 going into x squared plus 5x plus 4. And we'll just simply start by asking ourselves, what do we take times x to get x squared? And that is x. X times x is indeed x squared. X times 3 is 3x. We will change the signs. We will add down. Gone are the x squareds, leaving 2x, and bring the next term down, plus 4. Start over, rinse, lather, repeat. What do you take times x to get 2x? You take it times 2, so we're going to put a positive 2 up here. 2 times x is 2x. 2 times 3 is 6. We will change the signs and add down. And we get negative 2 for a remainder. You know you're to the remainder when you have the item that's left is below what you're trying to divide by. So the constant down here is below the level of an x term up here. So the remainder is negative 2, and we're going to place that on top of what we were dividing by, x plus 3, and thus that is our answer to the division. Okay, 34, long division, being very careful because we're missing terms in between the beginning and the end of each, what we're dividing by and what we're dividing into. So x squared plus must hold a place, 0x plus 1, heading into x to the 4th plus 0x to the 3rd plus 6x squared plus 0x's plus 10. Now that we have that all accounted for and all the places are held with zeros when those weren't there, we are really good to get going here. What do you take times x squared to create x to the fourth? And that would be x squared. X squared times x squared is indeed x to the fourth. X squared times 0x, however, is 0x to the third. Notice planning lined up those thirds. X squared times 1 is x squared. We will then change the signs of all of these terms and add down. So we have no x to the fourths. We have no x to the thirds. We have 5x squared. Now, because we were dividing by 3 terms, we will bring, or want to have, in our next setup, 3 terms. So we'll bring down the next 2. And we'll start over. What do you take times x squared to get 5x squared? I think of 5. A positive 5. 5 times x squared is 5x squared. 5 times 0 is 0x. 5 times 1 is 5. And we'll change the signs. And we'll add down. Very repetitive process. 5x squared minus 5x squared is 0. 0x minus 0x is 0. And 10 minus 5 is 5. That being the remainder, we will just simply come up here and say x squared plus 5 and 5 over x squared plus 1 is the answer to that long division. Okay, a little longer long division problem, but all the terms are present, so we don't have to include any zeros or anything like that. So we'll just get started here. What do you take times x squared to get x to the fourth? I believe x squared. X squared times x squared is x to the fourth. X squared times 2x would be 2x to the third. X squared times 3x would be 3x squared. Change the signs. Add down. We should get no x to the fourth. We will have 1x to the third. We will have 3x squareds. And we want to bring down the next term so that there are 3 to go on to the next step. And what do you take times x squared to get x cubed? I believe I'd want to take it times an x squared. Or an x, excuse me, not an x squared. An x times x squared is x cubed. X times 2x is 2x squared. X times 3 is 3x. Change the signs. Add down. We should have no x cubes. We should have 1x squared. We should have 2x. We'll bring down the 9, and we're going to finish this up one last time. What do you take times x squared to get x squared? Only a positive 1 will get you there. And positive 1 times x squared is x squared. Positive 1 times 2x is 2x. Positive 1 times 3 is 3. Change the signs one last time. And add down. And I believe we get a remainder of 6. Therefore, we will come up to the top up here, and we will have the answer of x squared plus x plus 1 plus 6 on top of x squared plus 2x plus 3. That being the remainder. Okay, we are getting quite a ways in to pre-calc here. Hopefully we are understanding what the question is here now. It says, what are the solutions of the equation p of x equals 0? That is saying basically, when is the function y have a value of 0? And we know y has a value of 0 at these x-intercepts. So I believe the answers are -5, -2, and 4. What is the question on number 37? It says, what are the zeros of the function? Well, you know what? The zeros and saying p of x equals 0 are exactly the same thing. So this question and the one before it are asking the same question. What are the zeros of the function? So it would be -6 and -1 and 4. What is the question here on 38? The question is when is this function, p of x, when is it less than 0? That is, when is y's value less than 0? When is y's value negative? Okay, so let me circle that. Y would be negative here. Y would be negative here. And so we state that in intervals. Seems like as we go from negative infinity to negative 5, and pick up again at, looks like negative 2 to 4, we would have all of the areas where the graph is below the x-axis, that is where it is, where y is negative. So the answer looks like it is, A? All right, we saw a question like this on the last test when we were solely working with quadratics, but now we've upped the game to higher degree polynomials. But this one is just a quadratic, so we could have seen this question on the last test. These are the zeros, these are the answers. What did they look like prior to becoming to us as answers? So in order for 1 to be an answer, it must have come from x minus 1. And in order for negative 5 to be an answer, it must have come from x plus 5. Those are the factors of the polynomial I'm seeking. Let's FOIL this out, and to FOIL this out, we get x squared plus 5x minus 1x minus 5 equals 0. Therefore, we get x squared plus 4x minus 5 equals 0. And this is the polynomial of least degree that has 1 and negative 5 as solutions. Okay, so if one of my potential zeros is, let's say that 3, the factor was x minus 3. If one of my zeros was at minus 2, the factor was x plus 2. If one of my zeros is 0, then I have to have a factor out in front of all that that's just x. And now the best way to probably put this all together is to FOIL the two binomials first. So we'd have x squared plus 2x minus 3x minus 6. So we'd have x squared minus x minus 6. And then simply distribute the x through to get x cubed minus x squared minus 6x. Okay, so by having a multiplicity of 2, that is telling us that that is a 0 twice. So I would have an x plus 2 as a factor, and another x plus 2 as a factor, and an x minus 4 as a factor. So it doesn't really matter which 2 you start with, but you can only multiply 2 things together at one time. So let's pick these front 2 and FOIL that together. That'd be x squared plus 2x plus 2x plus 4, which would actually be x squared plus 4x plus 4, that then we want to multiply together with the x minus 4. Now remember, to multiply that together, you just got to make sure that every single term gets to meet every single other term. So we'll generate quite a list of things here. Okay, so let's start off with x squared times x would be x cubed. X squared times a negative 4 would be a negative 4x squared. 4x times x would be 4x squared. 4x times a negative 4 would be negative 16x. 4 times x would be 4x. And 4 times negative 4 would be minus 16. Like terms all put together, x cubed minus 4x squared plus 4x squared would take the x squared terms out. And minus 16x plus 4x would be minus 12x minus 16. Okay, I'm zoomed in here pretty close to 42, just to hopefully we don't graph any of these, hopefully, okay? What I realize is that I'm going to have zeros at 1, negative 2, and 0. So those will be x-intercepts of the graph. And if I think about just the lead term, that's all I need to know is what the lead term is, okay? If I had 3x times, let me back up here. If I had a negative 3x times x, I would have a negative 3x squared. If that then got taken times x, I would have a negative 3x cubed. There's my dominant term. So the end behavior would be down to the right, up to the left. So let's go looking for a graph that's down to the right, up to the left, and hits the zeros of 1, negative 2, and 0. Down to the right, up to the left for number 1, or for A? Nope. Down to the left, up to the right for B? Yes. Does it hit the zeros 1? Yes. Does it hit the 0, 0? Yes. Does it hit the 0 at negative 2? Yes. I'm feeling pretty good about B. Let's go check the others, though, just to make sure. Okay. Down to the left, up to the right on C? Sure. Does it hit the zeros at 1? No. Down to the left, up to the right, end behavior on D? No. So I'm feeling real good that the answer is B, and I did not graph that with my calculator whatsoever. Okay, now think about this one. This one is 3x times x plus 1 squared, so it would be x plus 1 twice. Okay? The zeros are negative 1, but a multiplicity of 2, because that's negative 1 twice, and 0. Now remember what a multiplicity or even multiplicity of a 0 means. That means it bounces at that 0. It doesn't pass through. So at this particular 0, it's going to bounce. Okay? Now think about this. 3x and x is 3x squared, and another x would be 3x cubed. What's the end behavior of 3x cubed? Up to the right and down to the left. That totally gets rid of C, and that totally gets rid of D. Now let's examine closely what happens at the negative 1. It's supposed to bounce. Well, at negative 1, sure looks like a bounce. It comes up here and it bounces back. So I think the answer is A. And what we realize about B is that it doesn't even have a 0 at negative 1 at all. So the answer is A. Okay, so let's try to identify the zeros while this is all factored. The zeros of this would be negative 1. The zeros would be positive 2. And we'd have to solve this one for 0. So if you need to pull that aside, you'd subtract 2 divided by negative 3. Find out a 0 is at 2/3. Okay, so looking for things that have zeros at those locations, and also looking that the dominant term, if we multiply a negative 3x, an x all together, we get negative 3x cubed, and that would be down to the right and up to the left for end behavior. And so therefore we're looking for a graph that goes down to the right and up to the left. That eliminates A, and that's about all. So now we're looking at the zeros. A 0 of negative 1 and 2, negative 1 and positive 2, and also 2/3. I'm thinking B looks pretty promising here. Negative 1 and 2 and about 2/3. So I think that's it. Just make sure that the others don't hit at negative 1, 2, and 2/3, and they don't. Okay, so what are the zeros here of this problem? The x out in front, that would have a 0 of 0. The x minus 1 would have a 0 of 1, and the x minus 2 would have a 0 of 2 3 times. Okay, so 3 2's. Now, interesting fact, we kind of talked about multiplicity, and a graph that has an odd, like only shows up as a 0 once, it passes right through a point. A graph that shows up twice kind of does this number of maybe coming up here and bouncing, so it doesn't really pass through. Well, a graph that has a multiplicity of any more than twice, and so if it's odd, we would come up here and it kind of changes directions as it goes through. So it kind of curves, okay? So that's kind of what's going to go on at 2 there. It's going to curve. So also keep in mind in behavior, well, an x to the third along with an x along with another x is going to have a dominant term of x to the fifth. So looking for up to the right and down to the left. Definitely isn't C. Up to the right, down to the left could be D, could be B. Definitely isn't A, okay? So now, looking for a 0 at 0. D does not have one at 0. B does, okay? So it's B, I think. And what we kind of saw there, if I get that writing kind of out of the way, I think I see it. It must pass through. We don't have a really good window, but it must pass through and then come back through at 2, because I'm not seeing that transition here that I would expect to see when 0 is, or excuse me, when 2 is a 0 3 times. And you don't have to know that. You can judge the right answer here by just seeing what the zeros are, and that'll get you there. But it is an interesting fact of what happens when a 0 becomes a 0 like 3 times or 5 times or so. Interesting graphs. Okay, maybe we remember from class that the possible rational zeros exist by all of the possible combinations of the factors of the lead term and the constant term. So let's start with the factors of 2, positive and negative 1, positive and negative 2. Let's start with the factors of negative 8, positive and negative 8, positive and negative 4, positive and negative 2, positive and negative 1. Those are all the factors of 8. So now what we do is we consider all possibilities of the constant factors put on top of the dominant term, the lead term. I'll just use lead and constant, okay? So 8 put on top of 1 would give me positive or negative 8 depending on which signs I used. 8 put on top of 2 would give me positive or negative 4. 4 put on top of 1 would give me positive or negative 4, but I already have that. 4 put on top of 2 would give me positive or negative 2. 2 put on top of 1 would give me positive or negative 2. I already have that. Okay? 2 put on top of 2 would give me positive or negative 1. 1 put on top of 1 would give me positive or negative 1. And finally, 1 put on top of 2 would give me positive or negative 1/2. So I'm looking at any answers that have all of those possibilities, which looks to me like it is B. So all of the factors of the lead term, 3, are positive and negative 3, positive and negative 1. All of the all the factors of the constant term, 27, are positive and negative 27, positive and negative 9, positive and negative 3, positive and negative 1. And now again, we're going to put the constant on top of the lead term, and any combination of that creates all the possible rational zeros. So positive and negative 27 on top of positive and negative 3 would be positive and negative 9. 27 on top of 1 would be positive and negative 27. 9 on top of 3 would be positive and negative 3. 9 on top of 1 would be positive and negative 9. I already have that. Positive and negative 3 on top of positive and negative 3 would be positive and negative 1. And finally, positive and negative 3 put on top of 1 would be positive and negative 3, but I already have that. Positive negative 1 on top of 3 would be positive or negative 1/3. And finish out with positive negative 1 on top of positive negative 1, and that is already positive negative 1, which I already had. So we're looking for the one that has all of those as potential zeros. Looks to me like that is A. Okay, in order to find all real solutions for this problem, we can do this in a couple of ways. We can either factor it or use the calculator. So, first method I'm going to show you is factoring it. What I notice is each term has a common factor of x. Since that's the case, I could take an x out and possibly factor this trinomial that then is created into x, and 3 and 2 make 5, and 6 and 1 make 5 too. But what I realize is that I have to use 2 positives or 2 negatives to get 6, but the only way I can add and get 5 is 2 positives. So I better use a positive 2 and a positive 3. So my solutions then are 0 and negative 2 and negative 3. The alternative way to finding those zeros, or the real solutions, excuse me, is to find the zeros of the graph from the calculator. Okay, so I might trim this window up a little bit because there's a lot of wasted space to the left and to the right. And now I can tell I'm going to find the zeros of that, that, and that. So second calc, 0. Let's go get that left one. Left of it, enter. Right of it, enter. Guess. One of the zeros is negative 3. Second calc, 0. Left of it, enter. Right of it, enter. Guess. Another one of the zeros is negative 2. Second calc, second trace, excuse me. 0. Left of it, enter. Right of it, enter. Guess. And the other one is 0. So that's another quick way to get the zeros. The only downside to the calculator in zeros is you must have the zeros on the screen, which we now know, if you have a proper window, to see that graph on, so we feel a little bit better about that. Okay, so on 49, to find all the real zeros, if you remember factoring by grouping, now this is something we didn't spend any time on in class, but if you remember factor by grouping, we could apply that here. So we could take out an x squared out of those first two terms and have x minus 8 left, and I could take out a negative 1 and have an x minus 8 left there. Now factoring by grouping says that in those groups there is an x minus 8 that is common, so I could take out an x minus 8 and have x squared minus 1 as what is left. Now x squared minus 1 is the difference of squares, so I could do x minus 8 times x minus 1 times x plus 1. So my zeros are 8, 1, and negative 1. Now it's likely that you don't remember factor by grouping, or maybe don't like factor by grouping, in which case then we can head to the calculator and graph it and find the zeros that way. Okay, so if we're going to find the zeros here with the calculator, we just entered in the y equals graph. Now, that window is clearly not the right window to have, because I know the end behavior of x cubed should be down to the left and up to the right. So somewhere along the way, this is going to drop off here and come back around and back up. I need to be able to see that. So I need to see more to the right and possibly more down. So more to the right would be maybe to 10, and more down would maybe be to negative 20. Let's see if we see this well. Well, partially. I have to look more down.
Joyce, moves our guy to the office, please. Joyce, moves our guy to the office.
So let's go to window, and let's go more down, negative, and it probably is going to be a lot more down, but I'm just going to use the doubling principle and see. Yeah, not even close yet. More down, negative 80. All right, this is a nice comprehensive window then. So what I'm going to try to do is find the zeros right there, and right there. Now you can probably estimate that it's -1, 1, and say 2, 3, 4, 5, 6, 7, 8. But let's find it by second calc, 0. I don't want to wait for my cursor to scroll this, so I'm just going to enter left of that 0 is -4. And you see that it commits me to a line right over here. That's clearly left of this 0. Now, 0 would be right of it, and -2 would be close. And actually it says it's -1. Okay, second calc, 0. I'm going to push the button 0, and right of it as maybe 3. And in between 0 and 3 is 2. And it says no, the 0 is at 1. And one last time, second calc, 0. Left of this 0 would be like 5. Right of this 0 would be, say, I suppose 10. And somewhere between 5 and 10 is 6. And it says no, it's actually at 8. So we can get the zeros from the calculator if we don't like the factoring method. Okay, so number 50 says find all the rational zeros and factor. We can do this in one of two ways. We can factor it as grouping, like we did maybe above. If you try that, we could take an x squared out of the first two terms. And that would leave me x plus 3. And I could take a -36 out of the second two, and that would leave me an x plus 3 as well. When these match, that's a common factor in both halves, so I could take out an x plus 3 out of both halves and have x squared minus 36 left over. Now x squared minus 36 is the difference of squares, so we have x plus 3 and x minus 6 and x plus 6. So my zeros are -3, 6, and -6. Now that method requires you to know how to factor by grouping, which we did not study in this class. Now you have done that before in algebra and advanced algebra and college algebra, so if you have those skills, by all means use them, okay? But what we can also do is use the synthetic division and get there, okay? So what I'll do here is I'll grab my calculator. I will graph x cubed plus 3x squared minus 36x minus 108, and look for 1 0. That's all I need is 1 0. And I did that on my calculator, and I found one of the zeros to be at -3. Now, if you go ahead and find them all while you're at the calculator that way, that's okay too. But what I'm going to do here is just use that 1 0 and the synthetic division process to knock us down a level so we can factor what's left. Instead of having to factor this 4-termed thing, we'll only have 3 terms when we're done here. So bring down the 1. -3 times 1 is -3, add together, get 0, multiply, get 0, add together, get -36, multiply, get 108, add together, get 0. This proves that -3 was indeed a 0. Now what's that tell us? Well, -3 was a 0 means the factor before it became a 0 would have been x plus 3. This is the stuff that's left over, knocked down one level from where we were, so it's now an x squared minus 36 because it says we didn't have any x's. Okay, and so we can say the factors are x plus 3, and now this difference of squares factors a lot easier than we were seeing before with that cubic polynomial. And so the zeros are at -3, 6, and -6 like that. And again, you don't even have to do that if you don't want to. You could use your calculator to find all the rational zeros as well. So I kind of threw this one in here on purpose because there are some people that don't really like the calculator's use. I mean, I don't know, for some reason seem to think it's a cheating system to getting the mathematical answer. But if you try to use factor by grouping here, we fail miserably because we take out an x squared and we get x squared minus 8. And gosh, there's just nothing you can take out of 5x plus 14 to end up at x minus 8. So, you know, it's working out. It's not working out. So what I'll do instead is I'll graph this. And in so doing, I found 1 0 right away to be at -1. So let's synthetically divide this by -1. 1, -8, 5, 14. Bring down the 1, -1, -9, 9, 14, -14, 0, which we knew because I saw that on the calculator that -1 was a 0. And now we are at x plus 1 being a factor, because when -1 is a 0, x plus 1 would be the factor that caused that. And this trinomial right here is 1x squared minus 9x plus 14, which factors into its own couple of binomials. X, how about 7 and 2 if they were both negative? And so now I can see that all of the zeros are -1, +7, and +2. Now you could also find all those zeros just by simply finding all the zeros of that graph. There are enough ways to do it that just because it wouldn't factor, we shouldn't be stumped and stuck and give up on that.